And okay, friends, it has been a very long time taking an English tutorial. Okay, so I'm going to take an English tutorial on what is the essence of calculus. Really, what does calculus really means? And you know that you have lots of things around happening around you. So when somebody is talking about calculus, they would be telling that it is just about a tangent that is traveling along a curve and it reaches a point and you have a tangent. Okay, tangent is nothing but it is a line touching any curve like a secant line. When you just keep on zooming it, you will reach a point where it will be touching the curve. Okay, this is called tangent. And in here slope, you'll have a slope, and that slope is and the slope is nearly called the dy, and this is dx. Okay, and that is nearly called the derivative. Like this they would be saying, but what is the real meaning of derivative? Okay, so you should know that. Okay, without knowing that, you could not understand the higher concepts of calculus. Okay, you could not understand the higher concepts of calculus. Okay, so let's see what is an derivative and what it does to do with. Okay, in here you can see that it is going in this way, and there are also, if you go to three dimensions, if you go to nearly three dimensions, what will happen? Okay, okay, like here you can see that the slope which is traveling along this curve, when you take a three-dimensional point, when you just move this x and y, you can see that that curve, you can see that in x and y it is only orthogonal. Okay, the plane is orthogonal, but when you rotate you can find the tangent at anywhere. Okay, you can find the tangent at anywhere. As you can see here, the tangent can be found any direction. So this is called directional derivative. The highest point would be gradient. Okay, you have to understand this. So let's go to the integration. What happens in integration? In an integration, these are number of squares. You only have a one square. Within the limit of minus 7.625, you increase the number of squares and you will approximate the area under the curve. So the area formula is length into breadth. So every triangle, every rectangle will yield to a number and it will go like this. But what is the reason of Jacobian we are using? Why do we use Jacobian? Then what is a Jacobian? So as you can see here, there are lots of reasons the people say that they are going to really use Jacobian. For example, when I trace a point here along this line, you can see here, no, it forms a curve. That means 1 comma 1 over here is 2 comma 2 or 2 comma 4 over here, and when it traces a point like this. Okay, a rectangle, a square over here forms a different kind of curve over here. This is done in this manner. Okay, then come back to this point. So why do we use this? So let me get to the point directly. Okay, this has been discussed in the Quora. Okay, you have an equation like this, sine x squared 0 to 2, but you cannot integrate this, so you are using Jacobian. In one dimensional case, u x squared, so you put u here, and for this dx you differentiate, and this is called a scaling factor. I will tell you why this is called a scaling factor. So when this these limits over here are being transformed to this kind of limit, the 0.5 over here in x becomes 0.25. That is, sine x squared is sine u goes to a uh, uh, new kind of axis, like here. Okay, so this is what is happening inside. Okay, so it transforms. Now there is a sudden explosion and sudden expansion and compression over here. As you can see, it compresses here and it expands, but not in the case of Riemannian. This, you can see that every rectangle is the same, but when you are using this kind of Jacobian, in the case of sine x squared sine u, this happens. So what shall I do, sir? What should I do? What should I do to control this expansion? Okay, the convergence of these rectangles, will they yield to a converged number, I don't know. So you are multiplying this with the thing, this 2x, which is the scaling factor. Okay. This also happens in the polar coordinates. Okay. Then please explain me what is happening. So now you have seen that there is a sudden expansion in some places and sudden contraction in some places. Okay. When I move this, you can see that the rectangle is expanding. Over here and all, it is very big rectangle. You can see that it is very big number. But when I decrease the del, that in here, when you just decrease the number of, increase the number of rectangles, like that, I am decreasing the del. The both number becomes the same. When I increase it, they differ. Okay. You say, you take it here, you just consider del A and del area. These both number are different, but when I decrease it, they become same. So what you can do is, as in the case over here, okay, as in the case over here, you can see that these rectangles, which when converged to a smaller part, when you introduce a scaling factor, the stretching of 2x, what will happen to them is, they will go to the same number and they will converge uniformly. The error will become reduced very slowly. So you can also see this in Cauchy-Riemann function. Okay, even in your Wikipedia format, you can see in this Cauchy-Riemann function, you can see that in some forms you have, for example, okay, for example, a curve like this, you will have a tangent over here and the tangent will converge. But in a complex number transform, if there is a point over here, it will take many paths. It will not only take a single path, it will take various paths. But finding a tangent for this is very difficult. So you can't use the tangent method dy by dx. So you have to use a Cauchy-Riemann method of matrix and it will yield to this. So Jacobian is the real derivative. The Jacobian is the real derivative, and this is why you use to control the stretching factor. Okay, I hope you find this video very useful. So please subscribe to our channel. I am telling you again, as you can see, when you take this rectangle to the various parts of the coordinates, you can see that it is being stretched and compressed in various parts. And when you just decrease it, the area becomes equal. Del A, the smallest area, and the area you are considering will become equal. Okay. So when you increase this, what will happen? So the Jacobian will converge at every point. As you can see here, it is 2.8, but this is called the method where you can consider a new kind of mathematics. So they will say that actually integration is the opposite of differentiation. It is not like that. Integration and differentiation are not opposite. You may consider them as inverses, but I can tell you one thing, because in Wikipedia article they have given it as inverse. But I can tell you one thing, integration and differentiation are not opposite, because if you differentiate sine, it gives cos. If you differentiate cos, it gives sine. It goes like this. But when you differentiate e power x, it yields 1. It should not true for only one case. It should be true for every cases. So it's not like that. So the true opposite of integration or the derivative is its boundary. It has been told in the Stokes theorem. So we will be visiting the Stokes theorem as soon as possible. So this is what I'm coming to tell you. In order to manage the unwanted stretching, to make the area, when it converges, every individual rectangle would converge to a same area and it will converge to a point, okay, to a area. So this is why we use a considerable scaling factor. So this word is not being introduced in any of the textbooks. Even Jacobian has its own applications in very advanced theories like machine learning, deep learning, neural networks, in which they introduce these techniques. Even in finite element you have. In finite element, as mechanical engineer, what we do is we need to maintain the Jacobian within 1. If it goes beyond it, there will be no convergence in the thing, or the error would become very higher in the convergence of the finite element analysis. It is one of the numerical methods to approximate a differential equation. So that's why we use, because Finite element is also an integration. We use Jacobian in that for stiffness and this matrices. And you have local coordinates to global coordinates transformation. In that we use that. So in order to make that convergent, you can see that Jacobian is used. So Jacobian, there is a expansion and compression in the domain of integration. To in order to converge everything equally, we use a common scaling factor, and that scaling factor is a Jacobian. And derivative is also a common scaling factor. So that's why we say Jacobian is the derivative. Okay, so thank you. I hope you find this tutorial very useful. Like, share and subscribe. This is the essence of calculus, and we will see fundamental theorem of calculus and how boundary is opposite to the differentiation. Okay, we will discuss about it. Okay, thank you.